Okay, let's continue with page 2. At the top of page 2 we have a statement which is heat and temperature are not the same thing. They're related, but they're not the same thing. For example, if someone were to tell you, I'm not feeling well, can you take my heat? Obviously that person's not feeling well. Or another example, suppose it's cold inside a room and you call the custodian. Now what would you say to that custodian? You wouldn't say, it's cold in here, can you send up some temperature? You'd say, send up some heat. So you and I both know that heat and temperature are related, but they're not the same thing. And the relationship is heat is the form of energy that can cause a change in temperature. So in symbols, H for heat leads to a delta T. Delta, the Greek symbol for difference. In other words, the temperature is going to change. There will be a difference between the T2 and the T1. Now, more specifically, again, heat is a form of energy. Temperature measures not the amount of heat or quantity of heat in an object. Temperature measures the average kinetic energy. Now, what does that mean? Well, remember, kinetic energy has to do with molecular motion, or the motion of particles, simply put, in an object. The greater the average kinetic energy, the faster the particles are moving in an object, and the higher the temperature will be. Heat, compared to temperature again, depends on the amount of matter. So the more matter you have, the more heat energy will be needed to raise the temperature of that matter. For example, it takes more heat energy to boil a pot of water than a cup of water. But once they're both boiling, they'll both be at 100 degrees Celsius. So the temperature is independent of the amount of matter. The bridge between heat and temperature, another way of saying this is kinetic energy. If you raise the heat, if you increase heat, kinetic energy will increase, which means the particles will move faster, and the temperature will increase. So if you add heat, kinetic energy increases. Particles move faster. And as a result, the temperature rises. Again, heat versus temperature. The units of heat energy, when we measure quantity of heat, is the joule. Units of temperature are degrees Celsius and Kelvin. You might want to note here that 1 kilojoule is equal to 1,000 joules. And we'll use that later in converting back and forth. And then when you want to convert between Kelvin and Celsius, at the back of your reference tables in table T, you'll find this formula, which is K for Kelvin equals degrees Celsius plus 273. So if you want to convert from Celsius to Kelvin, you have to add 273. From degrees Celsius to Kelvin, add 273. And then the reverse, from Kelvin to Celsius, you could subtract 273. And while we're here speaking about the relationship between heat and temperature, let's park on big C, which stands for the specific heat capacity. You might recall that the specific heat capacity of water is 4.18 joules per gram degree Celsius. You'll find this in table B under the constants for water. What this means is, as we have illustrated, if you have a gram of water in a cup, and it absorbs 4.18 joules of heat energy, then that water will undergo a change in temperature of 1 degree. And it doesn't matter what temperature you start. So again, this is a constant that we're going to be using when we calculate quantity of heat. You might recall Q equals M times C times delta T. The C there is the specific heat capacity. And we'll deal with this formula some more later. Let's continue talking about temperature in the lower half of this panel. Suppose you have two objects side by side touching each other. Which way will the heat flow? Heat flows from higher temperature bodies to lower temperature bodies, from high to low. So in this case here, heat is going to flow from A to B. A is at 50 degrees Celsius and B is at 10 degrees Celsius. And as a result, the temperature of A will decrease, while the temperature of B will increase. Again, heat is the form of energy that causes a change in temperature. Usually, when heat leaves an object, the temperature of that object decreases, which means its particles slow down. And when heat enters an object, usually the temperature of that object increases, which means its particles start to move faster. An easy way to remember this is that B says to A, "Hug me, baby, I'm cold." Kind of corny, but it works. Puts a little romance into the chemistry too. All right, let's continue. Now, the two thermometers that you need to know about are the Celsius and Kelvin thermometer. And to make any thermometer in general, you're going to need two marks on the mercury tube. So when Celsius started his thermometer, he started with a mercury tube that had no markings on it. To start his scale, he had to have two fixed points of reference. In other words, two marks in the mercury tube. And then he decided to make those marks using the freezing point and the boiling point of water. So he took this mercury tube that had no marks in it, and he placed it inside of water that was freezing. And the mercury, of course, dipped. It went down. And the water can get no colder as it turns from a liquid to a solid. And so he made a mark. And he called that mark 0 degrees Celsius. And then he placed the mercury tube inside boiling water. And the mercury rose. And he couldn't make the water any hotter. So he called that mark the boiling point of water. And since he wanted to divide his scale into 100 divisions, he called that 100 degrees Celsius. So the two fixed points of reference in the Celsius scale are 0 and 100. And since there's 100 divisions in between, this is also known as the centigrade scale. Centigrade. Now if we convert from Celsius to Kelvin as we did before, let's do that now. So we add 273 to the Celsius temperature, we get 273. And add 273 to the boiling point temperature, 100 plus 273 is 373. So you have the corresponding fixed points of reference in the Kelvin scale. And what you want to notice is that the distance here is the same. It's a difference of 100. So Kelvin and Celsius have the same change in temperature. Change in temperature for Celsius is the same for Kelvin. If it goes up by 100 degrees on the Celsius, it's going to go up by 100 kelvins on the Kelvin scale. The Kelvin scale is famous for its minimum, which is 0 Kelvin. 0 Kelvin is known as absolute zero. Not absolute vodka, but absolute zero. And absolute zero is theoretically the lowest temperature possible. What happens at absolute zero is all molecular motion, at least translational motion, stops. So all motion stops at absolute zero. So if all motion stops, that means kinetic energy, which has to do with motion, is zero at absolute zero. Now something else. The fixed points are also known as, aka, equilibrium points. They're known as equilibrium points because at 0 degrees Celsius, for example, both solid and liquid states can coexist. So at 0 degrees Celsius, you can have H2O, solid, in equilibrium with H2O, liquid. So 0 degrees Celsius is not only the melting point of ice, it's the freezing point of water. So where you have both states coexisting, it's known as an equilibrium point. We'll talk more about equilibrium in terms of rates when we get to that unit. But for now, think of the marks on the mercury tube as equilibrium points. And at 0 degrees Celsius, well, I should say at 100 degrees Celsius, already covered 0, you have another equilibrium point in which H2O, liquid, can coexist with H2O gas, which is commonly known as steam. Okay, let's go to the bottom of this page and let's talk about the phase changes, which you probably know by now. It's good to review what their names are. Again, there are 3 states: solid, liquid, and gas. And the difference between these states in terms of properties, first of all, should be shape versus volume. The shape of solids is definite, and so is their volume, and that's why they say you can't fit a square peg in a round hole. When it comes to liquids, liquids have an indefinite shape and a definite volume. So liquids take on the shapes of their containers, but not their volumes. Gases, on the other hand, are both indefinite shape and indefinite volume. What that means, again, is a gas will take on the shape and the volume of its container. So, suppose we have a square container. Let's say that container is 1 liter of a gas in here. What I'm saying is, if you transfer that gas to a larger container, let's say this container is 4 liters or 5 liters, that gas will occupy that space. In fact, the gas moves to occupy that space through a process known as diffusion. The gas diffuses. Now, of course, the gases will be more spaced out. Its particles will be more spaced out in a larger volume, but it will occupy that space. Now, again, what makes a substance a solid versus a liquid or a gas? Well, it has to do with the space between the particles. In the case of a solid, because the attractions are so strong, in fact, they're the strongest when you compare solids to liquids or gases, the particles are held more closely together. And the motion of those particles can be described as vibrating back and forth. In the liquid state, since the attractions are weaker, the particles are flowing. And in the gaseous state, because the attractions are the weakest, you could say the particles are flying all over the place. So solid, liquid, gas. Now, as we go from a solid to a liquid, that process is known as melting, or fusion is another term we use. The opposite of liquid turning to solid is freezing, or solidifying. Then, if a liquid turns to a gas, that could either be evaporation or boiling. The difference being, when it's boiling, you'll see bubbles. The opposite, when a gas turns into a liquid, that's known as condensation. And then there are the 2 phase changes that are often forgotten, and that is sublimation. Sublimation is when a solid turns directly into a gas. So let's draw an arrow from solid to gas, skipping the liquid state. Number then is 5 for sublimation. You may have had this demonstrated in class with dry ice. Dry ice is solid CO2. If you take dry ice and just leave it there on a table, that dry ice on its own will turn into a gas. It's CO2 solid. It's not H2O solid. So dry ice, since it sublimes, it doesn't get wet. It turns straight into a gas. G. Another example would be I2 solid, iodine crystals. If you heat them just a little, they sublime and they form this purple haze. If you're doing this inside a test tube, it's a great demonstration of just the opposite, because when those iodine vapors cool down, they deposit on the inside walls of the test tube. So the opposite of sublimation, going in this direction, number 6, is deposition. Also, another term you should know associated with evaporation or boiling is vaporization. We'll talk more about that later. We do calculations with the heat of vaporization, HV, and the heat of fusion, HF. All right, so you have your phase changes or changes in state. You have the differences between each state in terms of attractions, in terms of motions, and of course the overall properties in terms of shape and volume. Okay, that's the bottom of this page. We're doing good. Let's turn to the next page, which is page 3.